In this video, we're going over just a couple definitions of complex numbers. And remember, these are complex numbers which are in what's called rectangular form as a plus bi. A is the real part, okay, right here. So this is what's called the real part. And b over here is called the imaginary part. Now, when I say the imaginary part, I'm not referring to bi. I just mean b. So that's the imaginary part. Real part is a. So you can see in this first set of questions, these are pretty straightforward, right? The real part is just 3. The imaginary part is 5. Now we get into something a little more interesting called the conjugate. Well, if you remember what a conjugate is, we've seen this before in radicals, in trigonometry. Oftentimes you'll see it in complex numbers. A complex conjugate simply says change that plus sign to a negative sign. Or whatever that sign in the middle is, flip it. Okay, so this now becomes 3 minus 5i instead of 3 plus 5i. If you had a complex number of, let's say we had w equals, I'm just making something up here, 4 minus 2i, the conjugate, which I would write w with a bar over it, is just 4 plus 2i, right? Whatever that sign is right there, you're just going to flip it. So now we're going to do the product of z with its complex conjugate. This is where things get interesting. Watch what happens here. Z times z bar equals the following. 3 plus 5i times 3 minus 5i. Now, if you remember how polynomial multiplication works, we're going to do some FOILing here. Okay, we're going to first multiply 3 by 3. That gives me 9. And then we do 3 times negative 5i, that's negative 15i. 5i times 3, that's plus 15i. And 5i times 5i, that gives me negative 5i squared. Great. So you remember this is the difference of squares. Those middle terms, the minus 15i, the plus 15i, those are going to cancel each other out when I combine like terms. Gives me 9 minus 5i squared. Now remember, I squared is negative 1, so I can simplify this further into 9 plus 5, and that is 14. Interesting thing is, the imaginary part's gone. There's only a real number left, and that is what happens every time you multiply a complex number by its conjugate. You get rid of the imaginary part, and that's a very useful trick when you need to do something like rationalize a complex fraction. So, the product of z with its complex conjugate is 14, and here's where the modulus becomes very easy for us. All we do is square root 14. So this modulus is defined. This is a definition. Modulus is defined as the square root of z times its complex conjugate. All right, so that should get you pretty far. And now you see in this lower part, we're just going to be doing some practice with calculating the modulus. So if you want to zip forward, you don't have to do that difference of squares things every time. You can do it a little quicker than that, which is this way. If I have some complex number, a plus bi, then the modulus of that complex number is simply a squared plus b squared. There's a little formula for you. If you prefer to go by the difference of squares, that's fine. You'll end up in the same place. But I can use this formula here. Hold on. Get a square root over that thing. I can use this formula to pretty quickly do some examples. Let's say I want to know the modulus of w. Well, that is the square root of, in this example, see what a and b are? They're 3 and 4. So this becomes 3 squared plus negative 4 squared, which you might remember from triangles. This is a common Pythagorean triple, that's what we call it. This becomes the square root of 25, which is 5. So we've got a modulus of 5 for w. And z, if you want to do that one quickly, that is the square root of 20. Okay, you can't turn that into a nice number with no square root. It doesn't go nicely. You could turn it into 2 radical 5 if you want. I don't think there's much difference. Let's go ahead and do that. Just be a little more clear about this. 2 radical 5. And then the modulus of w times the modulus of z, well, this is just radical numbers times each other. So this is 10 radical 5. Now, w's w times z, this is going to be complex right here. Okay, let me emphasize what I'm working on right now. This one right here is going to be a complex number times a complex number, which is 3 minus 4i times 4 plus 2i. And there's no way around it. You're just going to have to FOIL this out, but it's not that bad. 3 times 4 is 12. 3 times 2i is 6i, and then you have negative 16i from the cross term in the middle, and then negative 8i squared from the looks of it. I'm going to combine some like terms. Plus 6 minus 16 gives me a minus 10i in the middle, and then minus 8i squared is plus 8. So in the end, I get 20 minus 10i as the result here. 20 minus 10i. Okay. Now the magnitude of that, remember, well, you don't remember because I haven't showed you this, but interesting thing is, if you were to take the what am I trying to say here? Basically, this and this are equal to each other. And let's prove it. The magnitude of w times z equals 20 squared plus, not 100, 20 squared plus 10 squared, which is equal to 400 plus 100. Sorry, keep forgetting that square root. So that's the square root of 500. Well, what's the square root of 500? Remember what 500 is. 500 is 100 times 5. So this becomes the square root of 10 radical 5. Where have we seen this before? We just did this a little earlier. Right? You can see that the modulus of w times the modulus of z is equal to the modulus of wz.